So chapter 10 is about moment of inertia, and this chapter is divided into 4 sections. In section 1 we will study moment of inertia, what is moment of inertia, how we can calculate moment of inertia, and in the next section we will discuss parallel axis theorem, which is also one of the most important theorem in engineering mechanics statics. Then we will go through radius of gyration, and then in the last section we will study composite areas. Okay, so what is moment of inertia? Moment of inertia is also called second moment. So moment of inertia of areas is geometrical property of an area which reflects how its points are distributed with regards to an arbitrary axis. So basically it's a geometrical property, and moment of inertia has two terms in it, moment and inertia. So let's just first define what is inertia, and then we will explain intuitively how we can understand moment of inertia. But for now we can understand that it is a geometrical property of an area. And how this geometrical property is calculated? It's calculated by understanding how its points are distributed with regard to any arbitrary axis. So what is inertia? Now, inertia is a property which is utilized frequently when we study dynamics, but for the case here, inertia can be defined as a tendency of objects to resist the change of state of rest or of uniform motion. So what is inertia? Inertia is basically a quality of an object or a rigid body, that when a rigid body is moving, then it would like to keep on moving. But if that rigid body is at rest, so it would like to keep on staying at rest. So if we will apply a force, it will try to resist that force and it would try to stay at rest. So this is how you define inertia. Now, what would be a moment of inertia? Now, we have already discussed moment in the previous chapters. So it is a moment of inertia. So it is a quality of a body that resists the moment. When you are applying moment on a body, then that would resist the moment. So any object that is resisting the moment is resisting because of this moment of inertia. So higher the moment of inertia, then it would be difficult to apply a moment and try to bend that object. So higher moment of inertia would mean that it is difficult to bend that object. So that's how you define moment of inertia, but mathematically it is represented by this equation. So this moment of inertia of area is also called second moment of an area. So remember, in the last chapter we were studying centroid, and centroid was first moment of any area, and the moment of inertia is most often referred to as second moment of area. So this is a second moment of area, and that's the general equation how you can calculate the second moment of area, which is also referred as moment of inertia of areas. Okay, so let's just try to understand how this moment of inertia of areas is related with other properties. So for example, this is a rigid body, and this rigid body has some area dA at a distance x and a distance y, and overall the area of this rigid body is a, and this is a distance r from that individual element dA. So how you calculate moment of inertia of this whole area? So all you have to do, this dA could be anywhere, so there are so many particles with dA, and you have distances x, y for all these particles. So moment of inertia can be calculated by integrating all these areas along with second moment of this dimension. So if you look at the moment of inertia along x-axis and moment of inertia on y-axis, then it is nothing but the second moment of this area along that axis. So for example, if you want to calculate moment of inertia along x-axis, so it is second moment of area. So for example, you have somewhere this point. So this is the distance y. So second moment of area would be equal to the moment of inertia. So moment of inertia I of x is equal to y squared dA, and moment of inertia along y-axis would be equal to x squared dA, and you have to integrate on an entire area. So basically this is just general mathematical formulation, and once we will do the example, then it will become clear how we can calculate the moment of inertia of different areas. Similarly, we can also calculate the polar moment of inertia if we are interested in defining this moment of inertia by using this r instead of the x and y. Then we can use this formula to calculate polar moment of inertia. So polar moment of inertia would be second moment of area around the radius, and if you do the mathematical formulation and use the geometrical triangular formulations, you can also understand that this polar moment of inertia, which is r squared dA, is also the summation of ix and iy. So basically, if you add moment of inertia along x-axis and moment of inertia on y-axis, then by adding these two terms, you can calculate the polar moment of inertia. Or you can also do the integral of radius with these areas, and you can also calculate the polar moment of inertia. Now there is another term called product of inertia, which is nothing but the product of x and y. So it is also second moment of area, but you have to take product of x and y with these areas. So that's how you calculate the polar moment of inertia. So these are just a few terms which are frequently used in engineering mechanics. The most important one is being area moment of inertia. Now let us do one example to calculate how we can determine this second moment of area or moment of inertia of different geometrical shapes. So this is one of the geometrical shape, which is square, and we know the centroid of square is somewhere in the middle, and this is x-axis, this is y-axis, so that's the centroid. Now in this example, we are going to calculate the moment of inertia. Now usually we don't need to calculate the moment of inertia for these shapes, because these we already know the formulas for second moment of area of these shapes already. For example, circle, we know about triangle, rectangle, and these kind of shapes. But for the sake of this example, let's just try to calculate what would be the moment of inertia of this square. But later in the example, we will only just directly use the answer to calculate the moment of inertia. Now we know if we want to calculate moment of inertia along x-axis, which is this axis, and we want to calculate moment of inertia along this axis, so moment of inertia would be equal to y square dA, as we have studied in the previous slides. So that's the formula. If we use this formula, we can calculate the moment of inertia of this square shape. So what is dA? dA is part of that complete area. So here, let's just say this is the dA. So how you will calculate dA is that dA area is length into width. So we have width b, and what is the length? The length is dy. Okay, so now we can calculate the integral. Now integral is from, so we have to integrate complete shape. So if this is considered 0, so it would be minus h by 2, it would be h by 2. So we have to integrate this, and b is a constant, so I can take this constant outside the integral. So it would be minus h by 2 to h by 2 y square dy. So if you take the integral, then you can use this y, and if you take the integral, you will get y cubed by 3, and if you put from minus h by 2 to h by 2. So h by 2 minus and h by 2. So if you do this integral, then you can get this ix prime, which is moment of inertia along x-axis, equal to 1 by 12 bh cube. So that's how you calculate generally, but generally you don't need to calculate, because if you know this formula, which is 1 over 12 bh cube for square, so you can just input the values and you can extract the moment of inertia for square. Similarly, if we want to calculate moment of inertia along y-axis, then it would be hb cube by 12. So whenever you have a square and you want to calculate the moment of inertia of that square or a rectangle, then you can just directly use these equations and calculate the moment of inertia of that shape. Now, this is okay when we want to calculate moment of inertia along the centroidal axis. So this is the centroid. So if we want to calculate the moment of inertia along the centroidal axis, then we can make use of these equations. But if we want to calculate the moment of inertia along any other axis, then we need to use the parallel axis theorem. So that's the idea of using parallel axis theorem. And let me explain again. For example, if we want to calculate the moment of inertia along x-axis, then it is bh cube by 12. But if you want to calculate the moment of inertia somewhere else, for example, along this axis or along this axis, which is very useful in some of the applications, for example, if you are designing beam, column, or any other structural component, or even if you are trying to calculate the moment of inertia for composite bodies or from some axis, you frequently need to use this parallel axis theorem. Okay, so what is a parallel axis theorem? A parallel axis theorem can be used to find moment of inertia of an area about any axis that is parallel to an axis passing through the centroid. So all this means is that if you have a moment of inertia, and if you want to calculate the moment of inertia, let's just say along this axis, so it has to be parallel to the centroid, but you can calculate the moment of inertia along any axis by using this parallel axis theorem. And this parallel axis theorem says that if for example this was the x prime, which was the moment of inertia passing from the centroid, which was calculated by this formula bh cube by 12 for the case of rectangle. Now we want to calculate moment of inertia along this axis, and this axis should be parallel to the centroid. And now if we want to calculate the moment of inertia along this axis, then we can do that by applying this formula, which says that the moment of inertia along new axis is equal to moment of inertia along the centroidal axis plus area of that shape multiplied by dy square. Now what is this dy square? This dy square is the distance from this centroid and the distance where we want to calculate the moment of inertia from. So that's how we calculate, and we're going to do one example, then it will become more clear how to calculate the parallel axis theorem based moment of inertia along any axis. And if we want to calculate moment of inertia along y-axis, then we can do it by using this formula. And also if we want to calculate polar moment of inertia, we can use polar moment of inertia formula, and we can also calculate the moment of inertia along any other axis. Now before going to the example, let us discuss radius of gyration. So radius of gyration is basically another measure of the distribution of cross-sectional area from centroidal axis. Now remember, moment of inertia was also a distribution of cross-sectional area from centroidal axis based measure, and radius of gyration is also one of the measure. Now radius of gyration has this unit length, and this quantity is often used in design of columns or other design of structural components in structural mechanics. So that's why I just wanted to highlight this radius of gyration. And radius of gyration can be calculated by these formulas if we want to calculate radius of gyration along x-axis, y-axis, or along any polar moment of inertia. And the moment of inertia is, since for example, let's just take an example of a rectangle again. So polar moment, moment of inertia of this rectangle is bh cubed by 12. So if you try to take out the units, the unit of b is, if I want to take the units in SI system, so it's a unit of length. So let's just say it's meter. Height would also be in meters, so meter cube. So the unit of moment of inertia is actually meter 4. So it's a length raised to the power 4. But for the radius of gyration, it's just 1 meter. For example, this is meter 4 because it's moment of inertia. This is meter square because it's area. So it would be meter square. So meter square, and you take the square root, you get meter. So that's the one of the differences between radius of gyration and the moment of inertia. But moment of inertia is also frequently used, and radius of gyration is also used in, for example, design of a column. Okay, so now let us do some examples, and by doing examples, it's gonna get clear that how we can calculate the moment of inertia of composite bodies. Now this is one of the composite body, and we are interested in calculating the moment of inertia of this composite body. Now the moment of inertia for individual bodies we already know. For example, for this rectangle, the moment of inertia along x-axis is bh cubed by 12, and along y-axis it should be hb cubed by 12. So you input the values and you can calculate the moment of inertia, but this moment of inertia would be along the centroid. And also for circle, we can calculate ix or iy would be equal to this pi by 4 and r square, where r is the radius, which is 25 millimeter. So these formulas are known actually for similar shapes. We already know these formulas, but what we are interested in is to calculate the moment of inertia for the whole composite bodies. Okay, so from here we can see that this is made up of two segments. Segment 1 is a rectangle and segment 2 is a circle. So if we can calculate the moment of inertia of this rectangle and subtract the moment of inertia of this circle from it, so we can calculate the total moment of inertia of this composite body. And this is what we are going to do here now. But since we want to calculate the moment of inertia along x-axis, not along the centroid, so we also need to use the parallel moment of inertia. Okay, so we will use parallel axis theorem in this case. So Ix, according to the parallel axis theorem for segment 1, so first let's just do this for segment 1. So for segment 1, the moment of inertia along this axis would be equal to moment of inertia of that rectangle plus dy square a. So what is moment of inertia of this rectangle? It's bh cubed by 12 plus dy square. What is the distance? Distance is 75. And what is the area? Area is 100 multiplied by 75 plus 75. So it would be 100 multiplied by 150. So what is b in this case? The b is 100 multiplied by height is 150 whole cube by 12 plus 75 square into 100 into 150. So if you do the math, you can calculate Ix is equal to 11.4 into 10 to the power 6, and the unit of moment of inertia is millimeter 4, because all these values are in millimeters, so it's millimeter 4. So that's the moment of inertia for segment 1 along x-axis. Now let's just do for segment 2. So segment 2 is equal to Ix is equal to Ix prime plus dy square a. What is Ix prime? Ix prime for circle is pi by 4 I square. So pi by 4, what is r? R is radius, 25 square plus dy. So what is dy in this case? Dy is also same, which is 75 square plus what is area? Area is pi r square. We know the formula of area of a circle, which is pi r square, and r is 25 square. So if you calculate this, you will get for segment 2, okay, let's just put it here. For segment 2, you will get the area equal to 11.4 into 10 to the power 6 millimeter 4. So this was not actually, this was for circle. So for rectangle, the if you calculate all this, so you will get 112.5 into 10 to the power 6 millimeter square actually. So that was for the circle. So this is the moment of inertia of rectangle. This is the moment of inertia of circle. So if we want to calculate the total moment of inertia of a composite body, so it would be the moment of inertia for rectangle minus the moment of inertia for circle. So the total moment of inertia would be 101 into 10 raised to the power 6 millimeter 4. So this is the total moment of inertia of a composite body. Now let us do one more example so that it will become clear how to calculate the moment of inertia. So let's just say we want to calculate the moment of inertia of this composite body along the x-axis. So here we have 3 segments. This is segment 1, this is segment 2, this is segment 3, and we want to calculate the moment of inertia along x-axis. So how we will calculate the moment of inertia along x-axis? Now I will just directly calculate, but first let me calculate for this segment A and D. So we know the moment of inertia is Ix prime plus dy square a. Okay, let's just talk about this area. Now 1 by 12, what is bh cube? Now base is 100 and height is 300 cube by 12 plus dy square, distance. So distance is from this centroid to its centroid. So this is the distance, which is 200. So 200 square into what is the area? Area is 100, this distance, into 300. So 100 into 300. So if you do the maths, you will get 1.425 into 10 raised to the power 9 millimeter 4. This is the moment of inertia along x-axis of this segment A. Now if you want to calculate the moment of inertia for segment D, it would be exactly the same, because B is same, H is same, and the area is same, and also the distance dy, centroid of this to the centroid of the axis we want to calculate the moment of inertia from, is also 200, so it's same. So we have to so for A also segment and segment D also, the moment of inertia along x-axis is same. So now we will calculate the moment of inertia along x-axis for segment B. So for segment B, Ix would be equal to Ix prime plus dy square a. And what is Ix square? Ix square is bh cube by 12 plus dy square a. Okay, so let's just calculate B. So B is from this distance. So this distance would be, first we have to calculate this distance. This distance is half of the 100, so it's 50 plus 250 plus this is also 250, and this is 50, so it comes out to be 600. So B is 600 multiplied by height is 100 cube divided by 12 plus dy square. What is dy square in this case? So we want to calculate the moment of inertia along this axis, and the centroid is also here, so dy square would be 0, so it's 0. So this would be equal to 0.05 into 10 raised to the power 9 millimeter 4. So that's the moment of inertia for B. Now what is the total moment of inertia? Total moment of inertia is moment of inertia of segment A, moment of inertia of segment A plus moment of inertia of segment B plus moment of inertia of segment C. So moment of inertia of segment A is 1.425 into 10 raised to the power 9 plus moment of inertia of B is 0.05 into 10 raised to the power 9 plus moment of inertia of point D, which is 1.425 into 10 raised to the power 9. So if you calculate the total moment of inertia of this composite body, so it would come out to be 2.9 into 10 raised to the power 9. So that's how you calculate the moment of inertia of composite bodies, and you can also calculate along the y-axis, and you can also calculate for other, for example, like polar moment of inertia. So this is chapter 10. So see you in the next chapter.